Okay, welcome everyone to our OpenSim webinar. So my name is Jennifer Hicks. I am the R&D Manager for OpenSim and also the Associate Director of our National Center for Simulation in Rehab Research here at Stanford University. I'll be serving as the moderator for today's webinar. I'm pleased to welcome today's presenter, Apurva Rajagopal, who is joining me here at Stanford. She'll be presenting musculoskeletal models deconstructed. So OpenSim is a freely available and open source software application for visualizing musculoskeletal structures and simulating the movements of both humans and animals. So the first goal of our webinar series is to showcase the types of cutting-edge research that's being performed with OpenSim. OpenSim is also a large and geographically diverse community of users. So the second goal of our webinar series is to provide a platform so that members of the OpenSim community can form new collaborations and communicate their research with others. Before we get started, I have a few reminders about the format of the webinar. We'd love to get your questions after the talk, but we'll take those at the very end of the presentation using the Q&A panel in WebEx. If you need any additional technical help, you can consult the guide on our website for the webinars or send us an email or use the WebEx chat interface. Now I'd like to go ahead and introduce today's speaker. So Apurva is a PhD candidate here in the Neuromuscular Biomechanics Lab at Stanford. She got her BS in Math from Stanford and her MS in Mechanical Engineering also here at Stanford. She's an expert OpenSim user who has experience helping the OpenSim community through a series of several workshops and conference tutorials. And today she's going to be telling us about the various components and parameters in her musculoskeletal model and how you tune and validate and understand all of those key components. So with that, I will let you take it away, Apurva. Really looking forward to it.
Thanks, Jen, for the introduction, and thank you everyone for tuning in this morning. Today I'm going to talk about some of the basic components of a musculoskeletal model. I'll be using our recently published full body model shown on the left of your screen as an illustrative example throughout the talk. And hopefully this talk will give a nice overview for those of you new to modeling in OpenSim, and will have a little more detail for those of you with a bit more expertise. As we know, musculoskeletal models and simulation provide a non-invasive means to study components of human movement in greater detail than can typically be done with experiments alone. For example, using simulation, we can study how knee joint contact loads, plotted here on the vertical axis, change with increasing knee flexion and stance here on the x. And we can look at the muscle contribution to that load, which we can't examine with experiments alone. We can also use simulation to more efficiently design assistive devices to increase human performance. However, in order to have confidence in our simulations, we first need to understand the underlying components of a musculoskeletal model and to understand the effect of modeling decisions on our simulations. So in this webinar, we will use our recently published model as an example to, one, introduce the major components of a musculoskeletal model in OpenSim, and two, show how to use a simulation to validate a model for an intended application. So let's start with a brief overview of how we generate movement. First, we start with a neural command to our muscles. This filters through the musculotendon dynamics to generate a muscle force. These forces generate moments about our joints, which in turn accelerate our limbs and produce an observed motion. In a typical motion capture experiment, we can measure neural commands using EMG, and we can measure movement kinematics using markers or other sensors. However, we need either more specialized means or a musculoskeletal model to really gain insight on these blocks in between. So that brings us to an outline of the talk. I'll start by going over components of a model, including rigid bodies, joints, and the force-generating elements of our model. I'll then talk about some examples of how to validate a model in context of its intended use. So let's dive right in and talk briefly about rigid bodies. The dynamic behavior of a rigid body in OpenSim is really defined by the body's mass and inertia tensor about the center of mass. So for example, here's a body with mass 11 kilograms. And to describe the inertia tensor and center of mass location, we choose a coordinate system shown here in blue and assign values to these parameters with respect to these axes. Optionally, we can also assign visual geometry to the body. For example, the parameters used here describe the pelvis body in our model. And while this visual geometry doesn't affect the dynamic behavior of the body in any way, it's useful as we construct and visualize results with our model. So a model in OpenSim is made of multiple bodies, each with the properties described here. So for example, we can have a pelvis and a femur. And now let's talk about joints, which really define how bodies in OpenSim interact. So what we just described in blue were the body coordinate systems. And to define a joint, we additionally define a joint coordinate system on each body, shown here in green. The joint coordinate system can, but doesn't have to overlap with the body coordinate system. So for example, here in the pelvis, we have the body system in blue and the joint system in green. With the femur, both of those systems overlap. So specifically, we have a joint frame on the parent body, in this case, the pelvis, and a child body, for example, the femur. And once we have these, we can bring the two bodies together by aligning the parent and joint frames as such. We next define the degrees of freedom, or coordinates, that parameterize the motion at the joint. And these degrees of freedom define the transformation matrix between the child and parent frames that will determine the relative orientation of the two bodies. So for example, in this case, we may want to define a 3-degree of freedom hip joint between the femur and the pelvis, and we want to parameterize those by hip flexion, hip adduction, and hip rotation. We can continue this process of using joints to link bodies together to build the underlying rigid body system of a whole model. Notice that by doing this, we specifically choose what degrees of freedom to enable in the model. For example, we modeled the knee here as a 1 degree of freedom joint. And now, what does that mean exactly? Well, there are 3 bodies at play here, the femur, the patella, and the tibia. And if we wanted to use a maximal formation, we can introduce 6 degrees of freedom to model the patellofemoral joint, to model the rotation and translation of the patella with respect to the femur. And we can introduce 6 more degrees of freedom to model the tibiofemoral joint. Now, this may be important if, for example, you want to model the distribution of tibiofemoral contact forces. However, without careful validation, motion in many of these degrees of freedom may be noisy and difficult to simulate. Alternatively, as we did in our model, we can use a minimal formation and just use 1 degree of freedom, knee flexion, to define both of these joints and parameterize all other motions, such as translation of the patella along the femur, using just the knee flexion angle. And while this may give us less flexibility to track, for example, the knee varus angle independently of knee flexion angle, this formulation is more robust to measurement noise. Oh gosh. Ultimately, it's up to the modeler to decide what degrees of freedom are important to capture in a model for the research question you're trying to answer. So that wraps up all I'll say about joints. Let's move on to talking about the force-generating elements in a model. A model can include many different actuators. In our model, we used muscles to actuate the lower extremity, and we used torque motors to actuate the upper extremity. There are a whole host of other elements one can include, such as passive structures to model ligaments or contact geometry to model the interaction between the model and its environment. And I won't discuss them here, but if you're interested, the OpenSim documentation includes a description and examples of these. For today, I'll be focusing this section on how we model muscle. There are a lot of components to modeling muscle, so let's go ahead and start with a brief overview. On a high level, we need to model a muscle's path, and we need to model how a muscle generates force. And I'll talk about both of these in just a second. We'll talk about the model and some inherent assumptions. Then we'll talk about how we choose and validate the parameters in the muscle model. And finally, we'll talk about the consequences of muscle modeling assumptions in simulation. So let's start with the model. To model muscle geometry, we use a one-dimensional muscle path, or a line from the muscle origin to the muscle insertion, that represents the path of the muscle through the centroid of the muscle cross-section. So shown here, we have a snapshot of all of the muscles in the lower extremity in our model. We specify the path using either fixed points, for example, highlighted here in yellow, or using a wrapping surface, for example, shown here in blue. We often represent muscles with broad attachments, such as the gluteus medius, using several lines of action, as shown here. The muscle path determines the muscle moment arm, which ultimately determines how muscle force is converted to a joint moment. Specifically, joint moment is muscle force multiplied by muscle moment arm. And to validate our muscle path, it suffices to compare the moment arms of our model muscles to experimental data. For example, here we look at the knee flexion moment arm on the y-axis of the medial and lateral gastrocnemius with respect to knee flexion angle here on the x-axis. Our model knee flexion moment arms are shown with the solid blue and red lines, and the dotted lines in the x's represent experimental data. And we do this comparison and look for good agreement between our model moment arms and the experimental data. To model muscle force generation, we use a hill-type model of the muscle tendon unit. So this single path that we see when we define our geometry path is comprised of a tendon in series with muscle fiber. Similar to the one-dimensional path, the hill-type model here lumps the 3D volume of a real muscle into a one-dimensional tendon and a single muscle fiber. And I'm going to quickly go over some of the parameters in the model that we'll come back to later. So we have FT and FM, which represent the force in muscle fiber and muscle tendon and muscle fiber, respectively. We include a parameter alpha that describes the pronation angle of the muscle fibers with respect to the tendon, and this parameter determines how fiber force is transmitted along the tendon. We have muscle tendon dynamics that determine how the length of the muscle tendon unit, LMT here, is broken up into tendon length, LT, and muscle fiber length, LM. Now, the force in tendon and muscle is determined by three fundamental curves, parameterized by some muscle-specific parameters. So these are the three curves here, and we'll discuss them in detail. So let's go ahead through each of these curves and the necessary parameters. So we'll start with the contractile element. Muscle fiber force generation has both an active and passive component. The contractile element here in red describes the active component. The active force generating capacity of muscle is dependent on muscle fiber length, and the muscle generates its peak force, which we include as a parameter in our model, at its optimal fiber length, which is another parameter in our model. The active force generating capacity is also influenced by the shortening velocity of muscle. So beyond a peak shortening velocity, which is a third parameter, the muscle can no longer generate active force. This spring represents the passive force generating capacity of muscle as the muscle is stretched beyond optimal fiber length, and we have a curve that describes that. Tendon is in series with our muscle and is modeled as a nonlinear spring as well. So the force in tendon is determined by the tendon strain as the tendon is stretched beyond its slack length. So that's the fourth parameter, our tendon slack length. And finally, our model requires that muscle and tendon forces are in equilibrium. So the amount of fiber force that is transmitted to the tendon is determined by the pennation angle of the muscle fibers. And that will give us our fifth parameter in our muscle model. So that wraps up a quick overview of the model, and we introduced a lot of parameters along the way. So let's now talk about how to choose and validate those parameters. As a reminder, here are the 5 parameters we need to model a muscle. We need the maximum active isometric force, optimal fiber length, shortening velocity, tendon slack length, and pennation angle of the muscle fibers. To choose optimal fiber length in our model, we used experiments taken on cadavers published by Sam Ward. So the raw data includes muscle fiber length of the dissected muscle. So for example, the measurement shown here in green. Sarcomere length, which is taken using images of the dissected muscle. And pennation angle of the muscle fibers with respect to the line of action of the muscle tendon volume. So for example, this angle right here. We model our muscle fibers as a scaled sarcomere. So as such, to compute optimal fiber length, we assume that the ratio between sarcomere length and optimal sarcomere length, which we can get from experiments, is equivalent to the ratio between muscle fiber length and optimal muscle fiber length. So we use this relationship to solve for optimal fiber length. Similarly, we use a constant volume assumption in our muscle model to compute pennation angle at optimal fiber length based on the experimentally measured pennation angle. And our model publication has some more detail on this. Choosing the tendon slack length in our model is a slightly more involved affair, as this isn't a parameter we can directly measure. Instead, we rely on our model of muscle tendon dynamics to compute a tendon slack length. So to do this, we first pose our model in the same pose as the cadavers in the Ward study. For example, to compute tendon slack length for the psoas, we pose the model at 7 degrees hip flexion and 2 degrees hip abduction to match the cadavers in the Ward study. And now, once we do this, we have determined the total muscle tendon length of the psoas. What this doesn't tell us, though, is how much of that length is taken up by muscle fiber and by tendon. So our next step is to guess tendon slack lengths and then equilibrate the passive muscle tendon unit to match experimental data. So what does this mean exactly? Well, remember that passive muscle and tendon are just springs in series. When we pose the model, we determine the combined length of the muscle and tendon, but we don't know how much of that length is taken up by the muscle spring and how much is taken up by the tendon spring. And this distribution will be determined by the relative stiffness of the muscle and tendon. So going back to our curves, the stiffness of muscle is determined by optimal fiber length and the passive muscle force length curve. And the stiffness of tendon is determined by tendon slack length and the tendon force strain curve. Based off our experimental data, we know that for the psoas, for example, the passive muscle is at 1.2 times optimal fiber length, And now we can iteratively guess tendon slack length so that when we equilibrate our muscle tendon unit, our model normalized fiber length will match experimental data. So for example, if we started with a guess of tendon slack length that was too short and consequently have a relatively stiff tendon spring, our muscle fibers in the model will take up too much of the total muscle tendon length compared to experimental data. So we'll be further to the right on the force length curve. And so we know that on our next guess, we need to guess a longer tendon slack length. Alternatively, if we guess a tendon slack length that's too long and we have a relatively compliant tendon spring, our muscle fibers may not be as stretched as experimental data suggests. So in our next guess, we guess a slightly shorter tendon slack length. And we can iteratively do this until we narrow in on matching experimental data. Finally, the last parameter I'm going to talk about is how to choose optimal muscle fiber force. To do this for our lower extremity model, we used MRI imaging data published by Jeff Hansfield et al. And they showed that total lower limb muscle volume here on the y-axis scales linearly with subject mass times height. So we were able to use this relationship to determine the total muscle volume in the lower extremity for our model. They also showed that each individual muscle occupied a relatively constant percentage of the total lower limb volume between subjects. So we used that parameter here to compute optimal muscle fiber force per muscle. So using our single fiber model, we computed muscle physiologic cross-sectional area as individual muscle volume divided by optimal fiber length. And then we scaled this physiological cross-sectional area by specific tension. There's wide variability in reported values of specific tension for mammalian muscle, and ultimately we chose specific tension that was sufficient for our model to produce realistic muscle activity when generating simulations of gaits. It's worth noting that there's significant variability in the experimental data used to compute these parameters, and so we expect some level of uncertainty in the model parameters. We characterized this uncertainty for our model and reported them in our publication to facilitate future sensitivity analysis in simulations. Phew, okay, that was quite a long section, but hopefully that gave you a better idea of where some model parameters come from and what experimental data we need. We mentioned a couple of modeling assumptions along the way, and let's now talk about the consequences of these assumptions in simulation. The main assumption with our one-dimensional hill-type model is that all muscle fibers in a real muscle can be modeled as a single lumped fiber. So in other words, we assume that muscle fibers in a real muscle are at the same normalized fiber length and that all fibers change length uniformly. In reality, though, we know that this is not the case. For example, in a finite element model created by Sylvia Bumker et al., they looked at the muscle moment arm plotted on the y-axis with respect to joint angle on the x-axis. In simple cases, the muscle moment arm is equivalent to the change in muscle tendon length with respect to joint angle. So if all muscle fibers change length uniformly, we'd expect to see no variability in moment arm with respect to muscle fiber. And clearly this isn't the case. And in fact, in vivo microendoscope studies performed by Chen et al. Characterized the change in fiber length with respect to joint angle for the vastus lateralis. So their results are shown in gray, and for comparison, our model results are shown in red. And as you can see, our single fiber model overpredicts the length change in fiber length, and consequently also fiber velocity with respect to joint angle. Now, what this will do is this will exaggerate the force length and force velocity effects on muscle force generation. And this has consequences in simulation. So for example, let's look at the gastrocnemius, and a forward dynamic simulation of running. So at the time when the force demand on the gastrocnemius is the greatest, right before toe-off, the muscle is at roughly 55% of its optimal fiber length and is shortening at 25% of its peak shortening velocity. And together, these effects allow the muscle to produce at most 30% of its peak isometric force. Now, as I mentioned before, we ultimately chose the specific tension in our model such that our model could produce forces high enough to simulate dynamic activity such as running. And so partially because of this exaggerated force length velocity effect, our chosen specific tension was on the high end of experimentally reported values. By contrast, if we completely ignore the force length and force velocity effects on muscle force generation, we see that we require much lower muscle activity to produce the same force. And so we presumably could have used a much lower specific tension, closer to commonly reported values for mammalian muscle. This overestimation of muscle fiber length change also leads to excessive passive force generation, and we see compensatory muscle activity as a result in simulation. So for example, here we're looking at the knee extension moment with respect to percent gait cycle for the same simulation of running. The red is the active joint moment produced by muscle, and the blue is the passive moment. At the time of peak knee flexion in mid-swing, we see a large passive moment produced in simulations, and that's produced by the largely inactive quadriceps muscles. But to match the total required joint moment, we see compensatory muscle activity in the hamstrings that we don't see in the experimental EMG in gray. So that wraps up our discussion on how modeling assumptions can affect simulation. And in the context of this, let's move on to discuss how to validate a model in context of its intended use. So we want to check a couple of main ideas. First, we want to check that we're confident that the musculotendon parameters in our model are reflective or at least scalable to an individual subject. And for us, we ensured this by making sure that we derived our muscle tendon parameters from the most cohesive available data sets and scaled parameters when possible to our subject, as suggested by experimental data. We next want to check that our simulated muscle activity agrees well with experimental EMG. So we want to look for good agreement between the simulated activity in red and the experimental EMG in gray. And finally, we want to check that the muscles truly are driving the motion by looking for good quantitative agreement between our muscle-generated joint moments in the dotted red line and the total required joint moment in gray. So why do we do these things? Well, if we check all of this, then going back to our overall model of how we generate movement, we check that in simulation, we have the right muscles activating at the right time. We are confident that we have parameters that accurately describe how muscle activity generates muscle force. So that's a way of validating our musculotendon dynamics block. By comparing moment arms to experimental data, we're confident that our muscle geometry accurately describes how muscle force is converted to joint moment. And finally, by checking that in our forward simulation, the joint moments produced by muscles are sufficient to produce the observed movement, we check off the last couple boxes in our flowchart. So that just about wraps it up for the main ideas from today. I know we covered a lot of information. If you're interested in downloading the model and/or the data used to create the simulation results shown here, you can find them on our project page on simck.org. And we have a bit more detail in the publication as well about how we obtained and validated our model parameters. And with that, I'd like to thank my lab mates pictured here at the Neuromuscular Biomechanics Lab. They gave a lot of really great support and feedback while building the model as well as with this webinar. And with that, I'm happy to take any questions.
Okay, thank you, Apurva. That was really great. A ton of great information about how to build a model and how to gain confidence in simulation results from a model. So now we're going to open it up to questions from all of you. We have plenty of time for questions. To ask a question, find the Q&A button on your WebEx interface. Type your question in the box and make sure you select to ask all panelists. And with that, we'll go ahead and open it up to questions. While we're waiting for the audience questions to come in, I'll go ahead and ask one. So Apurva, the paper that you published was part of a special issue that was focused on reproducibility. Can you talk a little bit about what that process involved and how it changed the review process and additional steps and work you did to make sure the model results were reproducible?
Sure, that's a great question. So part of what we looked at for the reproducibility issue is making sure that all of the steps needed to create a musculoskeletal simulation were easily reproducible by our reviewers. So to do that, we wrote up really extensive documentation on each of the steps in the simulation pipeline, and we generated scripts that would allow users to auto-generate our simulation and our results figures, our simulation results figures. And so hopefully this is useful for other people who would like to, get a toe in on building their own simulations. It'll give a good example to start from. One of the interesting ideas that we found is also ensuring reproducibility across different operating systems and versions of OpenSim. So I think this was a really great opportunity to test that.
Great, thanks, Apurva. So now we have a question from Andrew Kazuski. First, he says, great presentation. Thanks for the great overview. His question is, what about the lack of 2D mesh and or volumetric muscle wrapping? How might that contribute to the validity of the current model?
So what really matters in how we generate and how muscle force is eventually transmitted to joint moment is the moment arms. So, and we did do a comparison of how our model moment arms compare to experimental data. So based on that, we are confident that we're transmitting muscle force correctly. You bring up a good point that our model really is a one-dimensional path, and it doesn't capture the full three-dimensional volume of muscle. And as I mentioned, there are consequences to that in simulation with how we model force length and force velocity behavior for the muscle as a whole.
Great. So now a question from Anton Felice. It says, thanks for the great talk. What are the main differences between the new model and the commonly used GATE 2392 model?
It's a great question. So we derived our muscle architecture parameters, so fiber lengths and muscle forces, from a bigger set of experimental data. So we're more confident that this model will scale well to a generic individual. The model also has better knee mechanisms so for example, between the femur, tibia, and patella to allow us to better compute joint contact forces at the knee. And finally, we did do a thorough check of this model in a forward dynamic simulation to make sure that the model is suitable for such simulations.
Okay, now we have a question from Adrian Lai. Again, thanks for the great presentation. You had a slide showing a discrepancy between the biceps femoris long head EMG signals and the model predicted excitations due to passive forces in the vastus lateralis during running. What's your opinion on how to correct this discrepancy, or if?
That is a great question as well. So one way to correct that is to change the passive force length behavior of the vasti, for example, specifically in the model. So we can make the passive force length curve for the VASI more compliant. And in fact, we can do that for any muscle. That is a parameter you can change in the model. We didn't do that in this case because we didn't have good experimental data that showed differences in compliance between the VASI and other muscles, although our simulation results may suggest that we should do that. So that's something you can change.
Great, thanks, Apoorva. The next question is from Sankalp Soni. So you talked about minimal joint formulation. So let's consider the tibiofemoral joint. The primary motion is knee flexion, and the rest of the degrees of freedom are dependent motions. How do you validate that the motion in other degrees is accurate?
Thanks for the question. So we parameterized the motion in other degrees of freedom, so like knee rotation and knee versus valgus and the translational components, using experimental data. So we're confident based on the published data that we captured at least the primary motions. We did a relatively good job of capturing how other degrees of freedom are coupled to knee flexion. It's not going to capture everything that you see in, for example, pathological gait, but that's a degree of freedom that you can open up if you need to.
Okay, thanks, Apoorva. The next question is from Ryan Okama. Is the lower limb model flexible enough to simulate tasks other than walking and running, for example, ice skating? What limitations would you expect to see in that context?
That's a great question. So by validating our model, or by testing our model using simulations of walking and running, we inherently tested the force generating capacity of model within some range of motion and within some level of expected acceleration. So in ice skating, for example, you might see much larger ranges of motion than you see in gait. So one of the things that you should check are how the muscle, if the muscle pads and moment arms are still valid in these larger ranges of motion, and look at, for example, how passive forces may start impacting your simulation at really extreme joint angles. Okay, so a nice follow-on question to that is from Danilo Catelli. He started using your model as soon as it was published, so an eager user. He's trying to apply it to a deep squatting trial. Eventually had to create specific wrapping to posterior hip muscles, but observed that passive forces for some muscles go to 0 during the movement. And also, while running static optimization has had some excessive quadriceps forces. Do you have any suggestions for how to troubleshoot or tune the model for the deep squatting task? I think as a general rule, especially when you're using the model for new applications, it's good to look at if there are specific muscles of interest in your motion. It's good to really carefully validate the path and the force generating properties of those specific muscles through the range of motion. So just visualizing is generally a good step, and doing some simple test cases that are not specific to your simulation is also good. So I would start there.
What do you mean by a test case, Apoorva?
I mean, for example, you could run a prescribed forward simulation where you just look at, for example, quadriceps activity in kind of in the range of motion that the knee flexion range of motion that you expect. And that might just be a good place to start so that you can understand when excessive forces come into play and which muscles are really affected, and you can look at what parameters in the model you might need to change or validate.
Okay, so we have one more question from Jan Thomas. It says, great presentation. And the question is, were the motor unit recruitment variations, so the neural commands, are those also captured in the model?
So the model doesn't explicitly have a model of orderly recruitment. There are parameters in the muscle activation dynamics model that parameterize the activation and deactivation time constants for a specific muscle. And we use default values for those, but that's definitely something you can change.
Right, and if you want to have some sort of neural controller so something that's generating what the muscle excitations are, that's a separate component. So you can estimate neural commands using the computed muscle control tool in OpenSim or static optimization, or you could write your own controller to generate neural commands as well. Okay, so this is your last chance to go ahead and if you have any more questions. Otherwise, we'll go ahead and wrap up the webinar. Okay. So thank you, everyone, for the really great questions and discussions. Thank you, Apurva, again, for an awesome talk, really informative, bringing up a lot of important issues in model building and testing. I want to acknowledge the support of the NIH and DARPA, which have provided funding for the OpenSim project. You can learn more about OpenSim at our website, including about future webinars and events. Please fill out the survey that's going to appear after the webinar ends so you can tell us how to improve the webinars and suggest topics for future talks. So with that, thank you everyone again. We look forward to seeing you at another webinar soon. Bye.